Welcome back to the drafting table. I'm super excited to guide you through this explainer brought to you by Forge College. So, in our last session on designing reliable deployment scripts, we actually laid the foundation and got our smart contract deployed. But today we're tackling the absolute lifeblood of decentralized apps, accepting funds. Because let's be real, a beautifully engineered, flawlessly deployed smart contract is, well, it's completely useless if its front door just hands your money over to strangers, or worse, locks it up forever. So we're going to learn exactly how to properly implement deposit functions in Solidity, and we're mapping it all out right here on the blueprints. Now, you might be wondering, what actually happens if your smart contract just forgets to count the money? I know, it sounds ridiculous, but it's a serious question. Imagine walking up to a highly secure, titanium-reinforced ATM built by top-tier engineers. You press a button, and before it even checks your balance or validates your card, it just starts spinning hundreds of dollars right into the street. Crazy, right? Well, that is literally what happens in Web3 when your deposit logic is flawed. If you don't count the money correctly, somebody else is going to gladly take it for you. So we're going to make sure that absolutely never happens to your code. To get us there, we've got a pretty solid schematic to follow today. First, we'll lay out the Secure Vault blueprint, basically how to safely capture that incoming value. Then we'll establish the golden rule of smart contract accounting. After that, we'll crack open our Solidity tools, actually write the code for the vault, look at where this is used in the real world, and finally, talk about how to harden that vault against attacks. It's going to be a great build. All right, let's dive right into our first step, the Secure Vault blueprint. We already built the walls of our application in our deployment lesson, but now we really need to engineer an airtight vault door specifically meant for incoming Ether. But before we start welding things together, we absolutely need to talk about the golden rule. This is the immutable law of physics for smart contract accounting. So there is this law, a literal golden rule, that governs our entire blueprint and prevents catastrophic leaks. Honestly, if you violate this rule, your vault will get drained. It really is that simple. It's called the checks, effects, interactions pattern. Okay, step 1, checks. You validate the transaction. Like, did they actually send the money? Step 2, effects. This is where you update your internal state, meaning you update your ledger to reflect the new balance. And finally, step 3, interactions. You only make external calls to other contracts after the ledger is completely updated. Just imagine the comedic disaster of updating your ledger after you've already let a malicious user interact with an external system. They could literally loop back around, deposit again, and trick the contract into crediting them multiple times before that first effect ever even registers. Always update your state first. Always. Okay. With that golden rule firmly in our minds, let's open up our Solidity toolbox and look at the actual hinges and locks we're going to use to build this thing. First up, we have the payable modifier. In plain English, think of payable as the reinforced slot on your vault door. If a function doesn't have this modifier attached to it, any transaction that tries to send Ether is going to be violently rejected by the Ethereum virtual machine. It's this amazing built-in safety mechanism. By explicitly labeling a function as payable, you're essentially cutting a slot in that door and telling the entire network, yes, I am intentionally designed to accept funds right here. So once that Ether actually passes through the payable slot, how do we know how much arrived? Well, that's where msg.value comes into play. You can think of msg.value as this built-in, completely untrickable scale that precisely weighs every single incoming deposit. It tells you exactly how much Ether, measured in Wei, was attached to that specific transaction. You don't have to guess, and the user literally cannot lie about it. The EVM itself guarantees that msg.value is 100% accurate. Now, as architects, we face a pretty interesting choice here. How do we actually want users to interact with our vault? On one hand, we could build an explicit deposit function. This shows super clear intent, but it does require users to specifically call that exact function, which adds just a tiny bit of user friction. On the other hand, we could use the receive handler. This acts more like a general receiving tray for any plain ETH transfer sent directly to the contract. It's incredibly convenient, but it can sometimes obscure the intent and make weird edge cases a lot harder to test. Generally speaking, the best practice is to actually have an explicit deposit function, and then just have your receive handler route any stray funds directly into it. All right, enough theory, let's roll up our sleeves, jump into the actual code, and do a teardown of a real smart contract vault. At the absolute core of our functional design is this mapping right here. It's a mapping of an address to a uint 256, and we're calling it balances. You can think of this as our internal, unbreakable ledger. It strictly and undeniably tracks who owns what. And we use uint 256 because it gives us massive, deterministic mathematical precision. So when someone deposits their Ether, their specific address is permanently tied to their exact balance, right here in this ledger. Now let's see how this actually builds out the logic inside our function. Remember our golden rule from earlier? Well, here it is in actual code. First up, the check. Require msg.value is greater than 0. We obviously don't want empty transactions wasting our space. Second, the effect. We take the user's address, which is message.sender, we look them up at our balances ledger, and we add that message.value to their account. And finally, we emit a deposit log. And hey, notice what is conspicuously missing here? There are absolutely 0 external calls. Checks, effects, log. Boom, done. It is beautiful, it's simple, and it's totally impenetrable. You might be wondering about that last line, though, the one emitting a log. In Solidity, an event is essentially like printing a vital receipt for off-chain auditing and reconciliation. The smart contracts themselves can't easily read these logs, but the outside world, like the front-end user interface of your decentralized app, is actively listening for these events so it knows exactly when a deposit actually succeeds. It's cheap, it's super efficient, and it's a really critical part of maintaining a fully transparent vault. So, where is this actually used? Let's zoom out a bit and look at some real-world applications of this exact blueprint. I promise you, this isn't just theoretical. You are going to see this exact pattern absolutely everywhere in the Web3 ecosystem. Just consider these 3 major sectors: escrow services, crowd sales, and staking contracts. An escrow service locks funds until a specific condition is met. A crowd sale accepts Ether to mint new tokens, and a staking contract locks up value to help secure a protocol. But here's the really fascinating thing. Despite having wildly different business logic, the foundational blueprint for their deposit functions is identical. They all rely on payable, msg.value, and that strict checks-effects interactions pattern to make sure the core math is completely bulletproof before any of the complex business rules ever take over. Okay, we've got a solid vault, but we can't stop there. Let's briefly talk about hardening the vault and looking ahead to future challenges. Look, I have a confession to make. Our current vault is incredibly secure, mostly because it completely avoids talking to the outside world. It takes the money, it updates its little ledger, and it just sits there. But modern decentralized finance, it is deeply, deeply interconnected. Which brings us to a rather terrifying question. What actually happens when our vault needs to interact with an external contract? What if we have to forward a fee or interact with a decentralized exchange right after a deposit happens? The exact moment we add external calls, our safe little vault is exposed to the wild. We essentially have to install laser tripwires. And that opens the door to our next major topic, reentrancy prevention, where we'll learn exactly how to stop attackers from tricking our vault into emptying itself. But for today, this is your foundational truth. Secure deposits demand strict ordering, checks, effects, interactions. If you can master this flow, you have engineered a vault that will absolutely stand the test of time. Thank you so much for joining me for this explainer brought to you by Forge College. I highly encourage you to head over to forge.college to continue mastering applied Solidity and, learn how to install those laser tripwires against reentrancy. Because in the dark forest of Web3, if your vault door opens outward to interact with a malicious contract, are you absolutely sure you can close it before it's completely empty? Catch you in the next one.